In the present video, we will be studying the dual nature of matter and radiations. The relation between mass and energy is equal to mc square given by Einstein completely changed the way the physicists used to look at energy and matter. According to Einstein's equation, energy can be converted to matter and matter can be converted into energy. So matter, that is material particles, they behave as energy as well as waves. Similarly, radiations, that is energy, behave as waves as well as particles. This is what we will be studying and exploring in this lesson. But before we come to that, an important topic which we have to study, the electron emission. Why do we need free electrons? Basically, all electronic devices, they operate with the help of electrons. Hence, we need free electrons for operation of a number of electronic devices. We know that the electronic devices, they have very high speed of action and they have very high degree of accuracy. The electronic devices like calculators, computers carry out precise calculations at extremely high speeds. The reason for accuracy and high speed of action is the electrons have a definite mass and always a definite charge, which means their interaction with the fields is always predictable. Similarly, the high speed of action is attributed to the extremely small mass of the electrons. That is why even a weak electric field gives them very high speeds, because the acceleration produced in the electrons is very large due to small mass of the particles. Although all matter contains electrons, but we make use of metals as chief source of electrons because the electrons are most loosely bound in the metals and they can be ejected from the metal surface by supplying minimum amount of energy. The energy needs to be supplied to the metal in order to eject the electrons, because the moment an electron leaves the surface of a metal, the metal surface will become positively charged and will tend to pull back the electron. Hence, we need energy to emit electrons from the surface of a metal. The minimum energy required to eject an electron from surface of metal is what is known as work function. The work function is expressed in a unit electron volt. Electron volt. It is the energy acquired by an electron when it is accelerated through a potential difference of 1 volt and is equal to 1.6 into 10 to the power minus 19 joule. The electrons can be ejected from metal surface by number of methods. The methods are listed as thermionic emission, field effect emission, secondary emission and photoelectric effect. The simplest and most widely used method is thermionic emission. It is the phenomena of emission of electrons from surface of metal when it is heated to a suitable temperature. The electrons emitted are called thermions and the phenomena is called thermionic emission. Another method is field effect emission, because this is the method in which the electrons are ejected from surface of metal by application of suitable electric field. Field effect emission, however, finds limited application because of low emission efficiency and requirement of large potential differences. Another method is secondary emission, when metal surface is bombarded by fast moving electrons called primary electrons. They knock out more electrons from the metal. The new electrons knocked out, they are called secondary electrons. And the most important method which we will be studying in detail in this lesson is photoelectric effect. It is a phenomena of emission of electrons from surface of a metal when it is exposed to electromagnetic radiations of suitable frequency. The electrons ejected by photoelectric effect, they are called photoelectrons. This is, however, important to note that electrons emitted by any of these methods, they are identical in all respects. We call them thermions, primary electrons, secondary electrons, photoelectrons, because of the different methods of emission. They are otherwise identical in all respects. Next, we will be studying the phenomena of photoelectric effect in detail. As already stated, it is the phenomena of emission of electrons from surface of a metal when exposed to electromagnetic waves of suitable frequency. Some metals like alkali metals with lower work value of work function are sensitive to visible light, whereas other metals they emit photoelectrons only when ultraviolet radiations are used. The experimental setup used for study of the phenomena is as in the diagram. We have an evacuated glass tube fitted with a quartz window. Evacuated glass tube provided with a quartz window. Quartz is required because it allows ultraviolet rays which are blocked by glass. S is a monochromatic source which allows radiations of a particular single frequency or wavelength. At the ends of the tube we have two electrodes. This is the emitter, which is photosensitive surface. Here we use a photosensitive metal. When light shines on this surface, it emits electrons. The photoelectrons emitted are collected by another electrode A called the collector. Any desired potential difference can be applied across C and A with the help of this potential divider arrangement. The commutator K, also known as reversing key, is used to reverse the polarities of C and A. That is, C can be made negative or positive with respect to A. The number of photoelectrons moving from C, that is emitter to collector, is a measure of the current here, or we can say the current gives us the number of photoelectrons flowing from the emitter to the collector. The electrons move from C to A, that is against the direction of the conventional current. Here study of photoelectric effect, we will vary various parameters, that is the intensity, the frequency and the potential difference one by one, and study the effect on the number, energy of the photoelectrons, etc. The first variator is the intensity. we will study the effect of intensity of incident light on photoelectric effect. For the purpose, we keep frequency fixed at fixed but suitable frequency. By suitable, we mean the frequency should be large enough to cause photoelectric emission from the emitter C. We also fix the accelerating potential we applied to the collector. Gradually increase the intensity of incident radiations and record photoelectric current. We plot a graph between the intensity along x-axis and photoelectric current along y-axis. The graph comes out to be a straight line, indicating that photoelectric current is directly proportional to the intensity of incident radiations, which leads us to a conclusion that number of photoelectrons emitted from a surface is directly proportional to the intensity of the incident radiations, provided the frequency of incident radiations is kept constant. Let's now study the effect of accelerating potential on photoelectric effect. We use light of a fixed frequency nu and a given intensity I1 and vary the accelerating potential V. Here from this graph, this side we plot positive potential applied to A, this side we apply negative potential to A. At zero potential, the anode gets a certain number of electrons, which is recorded as the photoelectric current here. If we make A increasingly positive, the photoelectric current is found to increase and attains a saturation value for a certain potential. Beyond a certain potential, there is no further increase in the photoelectric current because the anode potential is large enough to sweep all the electrons which are emitted by the cathode. So we get a saturated value of current. Here the current shows saturation. If we use this commutator to reverse the polarity, that is, if we make A negative, then it will repel the electrons from C. Only fast moving electrons will manage to reach the collector plate A. Hence the photoelectric current keeps on decreasing till at a certain value of potential V dot, which you call stopping potential. Obviously this will be negative with respect to plate C. At this potential, the photoelectric current drops to zero. It implies that even the fastest of the electrons, they are stopped at this potential. Or in simple words, the stopping potential is a measure of maximum kinetic energy of the photoelectrons. This is a very important result. The stopping potential is a measure of the maximum kinetic energy of the photoelectrons. Let's now study the phenomena further by increasing the intensity of incident radiations but keeping the frequency fixed. The graph obtained is shown here for a higher intensity I2 greater than I1. The graph shows that the saturation current increases with increase in intensity, but the stopping potential remains constant provided the frequency is fixed. The third graph shows a still higher intensity, a still higher saturation current, but the same value of stopping potential, indicating that the intensity does not affect the stopping potential, or the maximum kinetic energy of photoelectrons is independent of the intensity of the incident radiations. This is a very important result because classically it was assumed that the energy associated with light is a function of intensity alone. Here the results are otherwise. The kinetic energy acquired by the photoelectrons is not a function of the intensity. The wave theory had no explanation for this deviation. So the study of effect of potential leads us to the result that V naught measures maximum kinetic energy. We have work done by stopping potential V naught on electron equal to EV naught. This work is just sufficient to bring maximum kinetic energy to 0. Therefore, we have EV naught equal to K maximum equal to half m maximum velocity square. Now, one important result which we get is K maximum or maximum kinetic energy of photoelectrons emitted is independent of the intensity of the incident radiations. Now next we will study the effect of frequency of incident light on photoelectric current and the energy of the electrons. If you see the graph carefully, we choose three frequencies nu1, nu2, nu3 in that order, nu3 greater than nu2 greater than nu1. The intensities of the three frequencies are so chosen that we get same maximum current or same value of the saturation current. From the graph it's clear that higher stop frequency leads to higher stopping potential, that is for nu3 greater than nu2 greater than nu1 we have stopping potentials for nu3 greater than that for nu2 greater than that for nu1. That is, the maximum kinetic energy increases as frequency increases. The conclusion: larger frequency, larger stopping potential, larger maximum kinetic energy. Another important graph we plot between stopping potential, which is a measure of maximum kinetic energy, and the frequency of the incident radiations. For a given metal, say A, the graph happens to be a straight line meeting the frequency axis at nu naught. The graph implies, number one, V naught varies linearly with frequency. Second, for nu less than nu naught, that is if frequency is less than nu naught, V naught and hence the maximum kinetic energy will be negative, which is not possible. This is not possible. Hence, no photoelectric emission takes place for frequencies below nu naught called threshold frequency. The value of threshold frequency is characteristic of a given metal. As you can see, for metal A and metal B we have different values of the threshold frequency, and the threshold frequency is different for different metals. Now another important thing which we can notice from this graph is that for different metals A and B, the graphs have same slope, which we will be explaining later. This needs to be probed and we will study it later. An important observation which we have in addition to these observations is the moment frequency exceeds this threshold frequency, the photoelectric emission starts almost immediately. That is, the time lag between the exposure of emitter to the radiations, and the emission of photoelectrons is about 1 nanosecond or maybe less. That is, photoelectric emission is instantaneous process. Second, if frequency is less than threshold frequency, however large the intensity we may use, no photoelectrons are emitted. The results of the experimental study can be summed up as the following 4 laws of photoelectric emission. The first law: for a given material, there is a certain minimum frequency called threshold frequency, below which no photoelectric emission takes place, however large the intensity may be. Second law: for a given photosensitive material and a suitable frequency, the photoelectric current is directly proportional to the intensity of the incident radiations. Here, suitable frequency means the frequency exceeding the threshold frequency. Third law: for frequencies greater than threshold frequency, the photoelectric emission takes place without any time lag. That is, it's an instantaneous process, and the time lag is less than 1 nanosecond or less than 10 to the power minus 9 second. The fourth law is the maximum kinetic energy of photoelectrons is independent of the intensity of incident radiations, but varies linearly with increase in frequency. Having studied the phenomena in detail, let us see why the wave theory fails to explain photoelectric effect. The following points need to be considered for the purpose. Number 1, the energy absorption by electrons should be continuous. So the electron emission cannot be an instantaneous process. This is what the wave theory says. According to wave theory, the kinetic energy acquired by electrons, that is the maximum kinetic energy, should be a function of intensity and not frequency, because according to wave theory, the energy associated with light depends on intensity. Larger intensity implies larger energy. Therefore, the electron should be having a greater maximum kinetic energy if the intensity is increased, which is against the experimental result. Third important point is, according to wave theory, the threshold frequency should not exist, because if light of sufficient intensity is incident on a photoelectric material, it should be possible for the electron to gain energy sufficient for its emission by overcoming the surface forces. Einstein made use of Planck's quantum theory of radiations to explain the phenomena of photoelectric effect. According to Planck's quantum theory, light or electromagnetic radiations, they consist of photons, and each photon has energy E equal to h into nu, where nu is frequency of the incident radiations. Now Einstein opined that the energy h nu of a photon is either completely absorbed by an electron or completely rejected. No electron absorbs two photons. If the energy E of the electron is absorbed, of the photon is absorbed, a part of this energy is utilized for emission of the electron, and the rest is carried as kinetic energy. That is, photon energy equal to work done for emission plus kinetic energy. Further, if this work is minimum, that is equal to W naught, the kinetic energy will be maximum, leading us to the equation maximum kinetic energy equal to photon energy minus the work function equal to h nu minus W naught, or h nu minus h nu naught, where h nu naught is W naught, nu naught being the threshold frequency. The above equation, known as Einstein's equation of photoelectric effect, successfully explains all the laws of photoelectric emission. Let's see how. Number one, the photoelectric current is proportional to intensity. Now, according to photon theory, if intensity is more, it means number of photons is larger. Therefore, the chances of interaction of photons with electrons is large, and hence the photoelectric current increases. The second law, if frequency is higher, the kinetic energy of photoelectron will also be increasing linearly according to this equation. K maximum is equal to h nu minus h nu naught, which is another law of photoelectric emission. Then the photoelectric emission is instantaneous process, because the absorption of energy by an electron is a one-step process when the photon interacts with the electron. Once the energy is absorbed, the electron has to leave the metal surface. That is, the emission of photoelectrons is instantaneous. Moreover, if frequency is less than threshold frequency, that is nu less than nu naught, the kinetic energy of photoelectron will be negative, which is impossible. Hence, there must exist a minimum frequency nu naught, below which photoelectric emission is not possible for a given photosensitive material.